Okay, thanks everyone for coming. Leon surely needs no introduction around here. Today he's going to tell us about a very exciting topic. I guess it's based on your recentish paper or related to it um,
Yes, it is.
on
Yeah.
EN algebras in M+1 categories. So take it away
Okay.
when you're ready.
Yeah. Well, so thank you all for coming. Maybe a couple of things. Yeah, so this is definitely inspired by my recent paper on braid and stuff. And I think this paper will probably come out. It will be a two-piece, but they will come out around the summer-ish. Yeah. I don't want to write about it now. Anyway, but so today I want to talk about EN algebras in M categories. I'll get to exactly what those things are if you're not familiar with them. And yeah, so this is um forthcoming and it's strong work with Amartya, who is a undergrad in India right now, and he's really, really good. And the last thing I want to say before we get started is that I will have to leave at 2 sharp. Yeah. So keep this short and clean. Okay. But please feel free to ask any questions. Okay, good. So first, I want to just kind of give a motivation and kind of sketch out what the main results are going to tell us. And then maybe at the end, I'll give a sketch of the proof, but honestly, I don't really think we'll get there. Yeah. And once again, I want this to be kind of like, I know like things like in algebras and things like operad are not exactly things that a lot of people here are familiar with. So like, once again, like if you have any questions, feel free to ask. I'm happy to go as slow as necessary. Good. So are there any questions so far? So yeah, so Justin, I'm still hearing it.
Okay. I'm not sure what to do.
It's the, let me see. It's does anybody remember how to do this? So there's an option you can click where you hear a sound when people enter. You just want to click off that thing.
Yeah. Okay, I'll keep looking for it in the meantime, okay?
Okay, yeah, that's fine. Okay, good, good. So let's
Yeah.
get started. So the kind of the question of this paper is how can we explicitly construct EN algebras in M+1 categories? So first I want to kind of reintroduce what EN algebras and M+1 categories are. Okay. So to start there, I'm going to assume that everyone knows what a category is. So a category is just a set of objects and it has some set homomorphism between each object that composes. Great. So M+1 or M categories in general are just higher analog of this. So basically, instead of having a set of objects, you might have a groupoid of objects. Sorry, instead of having a set of morphisms, you might think you have a groupoid of morphisms or two groupoid or whatever. And in general, what we call M+1 category is that if you give me two objects, then the hum between them is M truncated. Okay, and maybe another way to think about this is to say that hum, if you want the inductive definition, C and D is M category. Okay, so that's another way to say this. So it's kind of an inductive definition. Okay, so for the expert here, since I'll talk about EN algebras, which only see the invertible part of a category, therefore the hum categories you only sees like the kind of the groupoid part, and that's why it's M truncated is already suffice as a space. Okay, does that make sense, everyone? But again, I think everyone's familiar with the notion of one category, and hopefully people have seen two category high before. Okay, good.
Sorry, Leon. Just to make sure here, you're thinking of by M truncated, you're thinking of the hums as like an infinity M.
Yeah. So the way
Okay.
the way I'm simply going about this is that I know what the infinity one category is, and then from that I can have a notion of a n comma one category, which is really what I'm working with right now. Yeah.
Okay.
Yeah. But for people who maybe just not really familiar with infinity category, just know maybe what the two category is, that's kind of way of thinking is also totally fine. But again, we'll only see like the n comma one piece of that because all the higher morphisms are equivalences. Yeah, but that's just a technical. Good, great. So now I want to kind of say a little bit about how do I point? How do I point in this thing? Okay, I forgot already. Okay, now I want to say a little bit about what the EN algebras are. Okay, so maybe starting with E1. So E1 is what we call monoidal multiplication. So just a monoidal structure. So for example, in set, it will be a monoid. In category, so we call monoidal category, and et cetera, et cetera. But basically, it's associative multiplication. Okay. And on the other hand, we also have E infinity, which is commutative associative multiplication. Okay. And in classical algebra theory, those are kind of your only two options, right? If you have an associative algebra, you can just ask if it's commutative. That's a yes or no question. But when you go to this more categorical, or people say more homotopic land, there's going to be a large range of things in between. Yeah. And those are characterized by En. Okay. And basically, yeah, and we'll see them very soon. So but that's kind of what this En are, and they're basically, this N is kind of telling you how commutative things are. Well, E1 means not commutative at all, and E infinity means fully commutative. Okay. So let's do this in the example of, let's do this in the example of a one category. Okay. So once again, so a lot of time in this kind of field, you're kind of off by one here. So here we're thinking about En algebra instead of a two category, and more specifically in a two category of one categories. So it turns out, the category of one category naturally forms a two category. So we're asking the question of En algebra instead of a two category. Let's just do it in cats. Okay. So to start, what do you need to define an E1 algebra? Well, first you need a tensor product. That's your monoidal structure. Then you need alpha, which is your associator. So alpha is an equivalence between X tensor Y tensor Z with X tensor Y tensor Z. Okay. But moreover, because you're in the category land, you also need something more, which is basically the pentagon axiom, which I hope most people have seen this before. Okay. And moreover, you're going to need actually a bunch of units things, but I'm going to try to suppress that in this talk. But they will come back later and they will play a very important role. Okay. Is everyone happy with this? So this is just kind of the standard definition of what a monoidal category is. Okay. So remember I said, when you study the classical theory of algebras, after you have a monoidal multiplication, you can just ask for the condition of it being commutative, right? It's X times Y equal to Y times X. Well, inside already in a two category, like the category of categories, that's no longer true. There's already something in between. Okay. So which is this notion of E2, right? And which, by the way, is like it appears in many parts of, math, say in representation theories. So for example, when people think about quantum reps, that's what appears there. Also, it appears very heavily in a lot of these modern, condensed matter theory. In particular, it kind of parameterizes what people call MTC, modular tensor categories. But these things very naturally appears also in physics. Okay, good. So let me tell you a little bit about what an E2 structure on a category looks like. Well, to start, you have to give me some sort of commutativity, and it's given by beta. So normally diagrammatically, people write it as a braiding over, just like this. So beta, but if you write it out, so beta is equivalence between X tensor Y and Y tensor X. Okay, and that's why you can think about it as a braiding. Okay, so because it braids, it takes one thing over the other thing. Okay. And you also need some more coherence condition. What the coherent condition are? Well, basically you need the two hexagon axioms. Okay, and I actually draw a diagrammatically here. So the idea of the hexagon axiom is to test if I braid X over, so over here I braid X over Y tensor Z, right? I can tensor them together. They can braid X over both of them at the same time. But over here, I'm first braiding X over Y. And then after I braid X over Y, I can braid it finally over Z. Right. And hexagon axiom, one of the hexagon axiom says they're the same thing. Okay. And the other one just reverse. So you kind of braiding under. You're taking braiding under two things close together. So I think that's braiding under the first one, then braiding under the second one. And those are your two hexagon axioms. Okay. Does that make sense to everyone? Okay. And lastly, in two-category land, then it turns out in two-category, then after E2, you just get to E infinity. So E3, E4, all of these things are equal to E infinity. Okay.
So can you just make sure I'm understanding this correctly? You're saying I have an EN algebra valued in two categories,
Yeah.
and after three and higher, it just becomes E infinity.
Yeah, exactly. So that's
So
C2 be a category. Then, well, I'm just writing symbols, but you can define something called the category of EN algebras. In C is equivalent to the category of infinity algebras. In C for n equal to 3.
Okay, very cool. Thanks. And
Good.
does this pattern just continue in the obvious way that you would guess?
Yeah,
If I
absolutely.
replace, okay.
Sorry, that holds also for infinity n categories and not only for n categories, or?
No, for infinity, En for any finite n is different from E infinity.
Okay.
If that's what you're asking.
Yes. Thank you.
Yeah. And that's, by the way, that's also why instead of one category, just like objects, for example, sets, E1, E2 is already the same thing as E infinity. It's the same thing. It's all given by this one. Yeah. Okay. So for example, in three categories, you're going to see 4 different layers. You're going to have E1, you're going to have E2, you're going to have E3, and then you're going to have E infinity. Does that make sense? And it just gets more broader and broader as your kind of category number goes higher and higher. Okay. Good. But to end things, let me just tell you what it takes for E2 algebra to be infinity. What additional structure you need? Again, not much. All you need is that the braiding is a symmetric braiding. So if I draw it out, all I need this thing. So I first braid x over y, then I braid y over x. I want this to be the same thing as just identity. Okay? So that's what you mean for braiding to be symmetric. And once you know the braiding is symmetric, then you lend it yourself with maximum commutativity inside of a two category. All right, any questions about this?
Yeah, Leon. So just one kind of notational or just how you call things. So in let's say I have so the top amount of monodality I can have in M category is always called symmetric, right? Like that.
Yes.
Okay. So, and for example, if I have a 3 category of 2 categories, and I want an E3 algebra, that's called syleptic. That's the naming.
Sorry, E3 would not be infinity instead of a 3 category.
Yeah. So it's syleptic. It's not symmetric.
Oh yes, yeah, exactly. I didn't know the word, but yes, exactly.
Okay. Yeah.
Yeah.
Okay.
Or it's construction to be. I'm not sure if that's proven. But basically, there's definitely a gap between E2 and infinity instead of a 3.
Right. Yes. Yeah. That's something I'm so a little bit confused about.
Very good. Yeah. So okay. So yeah.
Oh, just a quick philosophy question. Which way is this fact that E3 becomes E infinity and its generalizations, which way is it useful? Like is it telling me in problems, if you're just like out in the wild, am I using it to say, oh, I've got this big complicated EN algebra, but I can actually just pretend it's an E3 algebra? Or do I use it the other way? Do I say, oh, it's an E3 algebra and I can take advantage of all? Like, I'm just trying to ask which direction is this equal sign most useful?
So in fact,
that even answerable?
we'll use this later, or this is going to also show up later. But the way you can think about it is that it's on one hand, it's telling you that so one thing about E infinity that's hard is that all of this EN, I'll get to this. This is kind of the central point of the talk. But all of this EN, they are like really nicely built. They kind of can be built in this universal way. In fact, there's a statement called down additivity we'll see, which once you know E1, you can build all of them. But the problem is that you see this combinatoric, the combinatorics of this is not obvious at all. So for E1, as you will see, it will be there's people. The first person who introduced E1 knew how to do all of them. The same is already not true for E2. For E2, it's already kind of unclear why the hexagon's there. Okay, and you might say that's fine. But the next stage for E2 algebra, so if you want to define something like E2 algebra on 3 category, it becomes highly non-trivial. And many people have got it wrong before what the correct axioms are. Okay, so basically these EN algebras, they're like very nice conceptually, but they are hard to build. like give you these actions, like the ones I give you these data, like the ones I gave you here, to actually try to build them. So, but if you have a finite cutoff, and let's say you want to go to infinity, which is what most people want normally, just fully commutative, then at least you know there's a cutoff there. Once I reach this cutoff, then I'm kind of fully commutative. There's nothing else I have to check. So that's one we can think about it. The other way you can turn this around, and you can just say that, like, in lower categorical numbers, something like E3 basically is not that interesting, right? Because it's just infinity, right? It doesn't have like any interesting braiding. There won't be any interesting, like, if you think about it in physics, there won't be any non-interesting like long range behavior between whatever your expectations are, right? Because there's no braiding anymore. You cannot braid anything, right? But I think most of the time, at least in category theory and adjacent fields, you try to use the fact that E3 is infinity to give some maybe finite way to construct infinity things, because again, it becomes incredibly complicated, as we'll see.
Okay, thanks.
Okay, very good. Okay, good. Yeah, and again, that kind of nicely leads to the question which I want to answer in today's talk, which is how do you actually generalize this to M categories? So first of all, M categories, if I put an M here, right, there will be n+1 columns, or I guess n+1 row now, right? But what are those actual diagrams I'm going to write, right? Again, so I want to once again mention, so even in the case of defining an E2 algebra in three categories, so maybe confusing, but when people thought about it at the time, they would think about the three category of two categories. Okay, so you want to build like an E2 two category. And people, well, there were definitely accents that were being thrown around based on that, even with Wadowski and stuff. But the first couple ones were definitely wrong. There was a crucial action they missed, which people nowadays call S+ equal to S-. Okay, but again, I don't want to get too much into it. This is not exactly the route I'm going to take. But I do want to mention that, again, it's a very subtle question to actually what are the actual diagrams and conditions you have to satisfy to be an EN algebra. Okay, any questions?
Yeah, Leon, so would you say Gursky's axioms are not E2? Or are Gursky?
I don't know which one's which. The E2 algebra in a three category should have basically three different diagrams. There's two that everybody use, and then there's S+ equal to S-.
There are actually 4 axioms in Gursky's paper, so
okay, I don't, yeah. But.
Yeah, okay, fair enough.
Okay. So yeah, sorry, I'm actually not super clear on all the history behind it. All I can tell you is that this is the question we're asked, and I'm going to give an answer today. It's not in some sense, and we'll see what the answer is. It might not be like the computatorially most compact one. Well, actually, in some sense, it's very compact. In some sense, it's not, but it's a universal answer, and I guess I know for a fact it's equivalent to E2.
Okay, I like this. Nice.
So it will be different from the standard one we have, but it's equivalent. I checked that for this case. In the three category case, I haven't actually checked it, but I know at least whatever my version is it corresponds to an EN algebra in the sense of, like, I don't know, higher algebra, or like, in the sense of May and Borman-Waugh. Yeah. Okay, great. Any other question? Okay, good. So let's keep going. Okay, so first, let's do the simplest case, and the case that's really understand, which is E1 algebras, right? How do we even just define a monoidal structure, right? Some multiplication instead of M category. And in fact, that's already answered by the first paper on the subject, which is Stashev's 63 paper. Okay, so let me just kind of quickly review what Stashev paper said. So what he did was that he actually break E1 into he actually gave basically a bunch of subalgebra of E1. Okay, starting with E0. So first, let me remind. So these are like subalgebra structures. So the formal name, they are operads. So operads are things that parameterize algebras. But they think about them as encoding some algebra structure. So let me kind of give you the first couple cells of this. Okay, so what E1 is so E1 algebra encodes an algebra. So just a priori just an object C. Okay, just give me 1 second. Yeah, let me introduce some notation. So I didn't do it last time, but I want to introduce some notation. So let's take C to be my fixed M category. Okay, and C, the small c instead of big C is an object. Okay, and I want to think about algebras on this object. Okay, good. So what E0 encode is literally just an object C together with a unit, which is from the, let me call that unit epsilon, which is from the unit objects of C, of capital C into C. Okay, so you can think about this as a space whatever together with a point inside the space. That's it, nothing else. So very boring. Okay, not very interesting going on. And now let me tell you what E2 algebra is. So it consists of, first of all, E1 algebra. Okay, and moreover, it has a binary multiplication, which I'm going to call M from C tensor 2 to C. Okay, so again, we're going to kind of suppress the unit of structure in this talk, even though they're very important in the story. But basically, what E2, yeah, I'm going to do that very soon. But basically, takeaway of a A2 algebra is it's just an object together with a multiplication that happens to be unital. So it actually has some other unital data, which I'm not going to get into. Okay, and what the E3 algebra is, it's for C, it has the multiplication, but moreover, it has the associativity. Okay, and plus unital data again, but I'm going to suppress them. And what the E4 algebra is C, its multiplication, its unitivity, and the pentagon axiom. Okay, and plus units. Okay, but as you go up to higher and higher categorical level, it doesn't just end there. So it turns out there are basically these higher pentagons that you have to satisfy, and then satisfy, and satisfy, and all the way to E1. And in particularly, here's maybe an abstract way to show what Stashev says. So he says that when you go from AN to AN plus 1, so again, I'm kind of build structure. I'm adding more and more conditions and property and data it has to satisfy. You basically, what you have to fill in is you have to fill in, yeah, you have to fill. So basically, yeah. So what you have to do is you basically have to fill in a disk of this form. Okay. So I guess that's yeah. So you have to fill in n-1 cell here. Okay, in this space. Okay. So for example, when I go from A1 to A2, I have to fill in so s to the -1 just 0. I have to basically give a point in C tensor 2C, and that point is exactly the multiplication. Right? And now when I go from A2 to A3, what I have is I have an S0 worth already in C tensor 3 to C. Well, what are those? So S0 is just 2 points. What are those 2 points? So one point is just X tensor Y tensor Z. The other point is X tensor Y tensor Z. Right? Basically, if I give you a binary multiplication, those are kind of the 2 ways you can build trinary multiplication, a trinary multiplication for that. And what I have to do, so that's what I have already. I have to fill that in. So I have to just draw a line between them. And that's exactly associativity. Right? The next level up from A3 to A4, what I'm going to have is I'm going to have the boundaries is topologically S1. What you really, well, you form a pentagon, depends how you do it. But basically, it's like, I think everyone has seen this before. Okay. And I also don't think I can really get this correct. So this one is this. Right? Good. This. I'm so close. This. Yeah, there we go. Yeah. So you can. So basically, using associativity, if you have 4 elements, I can already make a circle worth of multiplication. And what I need to do is the pentagon fills in that circle. Right. In fact, we saw all of this when we were thinking about just what the monoidal structure is for a category. So instead of 2 categories. Right. But the point of what Stashev shows is that this pattern continues on. I'm not going to draw them, or there will be higher dimensional objects. I'm not going to draw them, but it continues on. And Stashev told us exactly how to build kind of these attached maps and exactly what we need to do to fill it in, and just keep going and going. Okay, very good. Does that make sense, everyone? So this is what people call, in mathematics, people call this, all of this combinatorial structure, they call it Stashev associahedron. And basically, you see what we want is we want a similar story to the associative, but not just for E1, right? But also for commutativity, for E2, for E3. And the answer is yes, we're going to have a very, very beautiful picture that generalizes this. Okay, good. So but let me tell you some features about this. Okay, so the first feature is that going from one cell to the next cell is what we call is N-1, N-3 connected. Okay, so give me a sec. Okay, and basically this connectivity level is basically about the dimension of the cells you're trying to fill in, right? So you see that when I go from A1 to A2, I have to actually give you a point, right? I have to give a new multiplication, right? But I don't have to give you any new multiplication after that, right? For example, from A2 to A3, I just have to identify two multiplication together, right? Two operation together, right? Which again is in some sense is less data. It's like a higher dimensional data. You're working with like a higher dimensional sphere. And then from A3 to A4, I just have to start filling in, planes, right? So that's like, again, I think maybe, yeah. So originally this talk was intended for a much more homotopic audience. Since I don't think that's the case, I'm just going to use a little bit more heuristic language here. So basically, I'm only filling in higher and higher dimensional spheres. And if you think about it like from algebraic kind of view, then I'm using kind of higher morphisms to do it. I don't have to introduce a new zero morphism or one morphism anymore. Yeah, and that's what it means for this to be higher and higher connected. Okay, and yeah, I think I'm just going to ignore that point. It's very subtle. The other point I'm going to ignore. Okay, good.
Sorry, can I ask you a question?
Yeah, of course. Yeah.
Is there a geometrical interpretation of these spheres?
Of these spheres? Yeah, I mean, like, I wouldn't say geometric. I think it's very much combinatorial. You can definitely, I mean, like, would you say this is geometric, like this picture?
Yeah, no, I see where this comes from. I'm just wondering if there is a deep explanation of why you have to consider consider like a filling of a sphere to a disk, stuff like that. Does the disk has any kind of particular meaning in some kind of sense?
I don't want to give you too much. I can give you a combinatorial description. So basically, every time, what you always have to fill is a polytope. So you see the things I'm drawing here, they're actually polytopes.
Yeah.
Right. AKA like they're really built out of edges and vertices and two cells, whatever. And it turns out every time you always have is you're going to have a boundary of a polytope.
Yeah, you're just filling, but I don't know what that polytope is trying to represent. That's my question, essentially.
Great. Okay, so the polytope I try to represent all the different ways you can. That's a great question. Unfortunately, it's a very key point. I cannot get too much into it. But what the polytope is trying to represent is all the different ways I can generate.
Yeah, that's fine. But like, which kind of objects describing your structure? That's like, yeah.
So the only thing I can really say is just that like the polytope, the boundary of the polytope is like all the different ways I can generate an n+1 morphism.
Yeah.
A in algebra, I want to make that contractible. Basically.
Okay, that's fine.
I want to say actually this is a unique n+1 morphism. So therefore I have to contract that space.
Okay,
and that's exactly why you're filling in the boundary of the polytope.
Okay, thank you.
So I think another nice way to say it is that if you just look at like n vec g, right? Where or m vec g, for example, where you want to describe like a G gauge theory in m dimensions or m+1 dimensions or something. So all this combinatorial data, you can write it as group cohomology, right? So for like A3, A4, that's like you give a cohomology class in H3 of G and also H4 of G, and then you can have like a some kind of tensor network or G defect network picture for that. So I think like that's how the associahedrons show up in that context, like explicitly as the defect networks that you decorate your space.
No, thank you for that. That's a very good answer too. Unfortunately, I'm just not super comfortable with that language, but absolutely can represent this defect networks. Okay. Any other questions about this? So again, this is kind of the base case. This is the case we know exactly what to do. And okay, so maybe I forgot to say this, but the theorem, because again, because when you go from AN to AN+1 is more and more connected, like you're filling higher cells. You can think about it either in field theory or in category, but basically if your category number is low enough, then those it takes even more dimension for those to fill in. So these are kind of trivially filled. Does that make sense? Yeah. So up to some point, you don't have to fill it in anymore. So okay. So I'm going to try to get the point correct, but I will never do. But basically, AM category algebra is equivalent to A infinity algebra. So let me write it this way. So AN. Sorry. So AN of C is equivalent to A infinity of C if, so again, C is an M category. So there's something between N and M. So let me try to get this correct. So let's just take C to be a 1 category, then A2 structure. So I'm going to try to say M plus 1. Okay, I'm going to say M plus 2. Is that correct? Hank, do you know? You need the A2 structure. You need associativity too. So you need the A3 structure. Yeah.
Right. Yeah. I think that's N larger than M plus 1. Yeah.
Okay, great. Yeah, exactly. So now combine this fact, right, which is coming from here. It's just coming from this factor here. So combine this fact with the explicit combinatorial description of how to lift one to the other. I can always tell you exactly what it takes to give a E1 structure, right? Because in an M category, I just have to go up to AM plus 2, and that just means I just have to iteratively fill in the Stasher association up to the M plus 2 association, and I'm done, right? And for example, that's exactly how we were able to write on this, and the higher categorical analog for this for any category. Okay, does that make sense? So again, the E1 case is done, by Stashev all the way back in 1963. Okay, are we still good so far? Good. Okay, so maybe another thing to think about if you think about like defects with more topological order, one we can think about it is that so maybe this is Justin also said a little bit about this earlier, but basically like things like defects, they can fuse together. That the fusion of defects very naturally give like a EN algebra where I think N is the codimension of the defect, because that's the kind of number of direction I can fuse things in. Okay, and then once you know that, then you know kind of abstractly already it has to be in algebra just because of the kind of the geometry or the dimension of the problem. Then all of these structures you can think about are basically they are like data or properties the defect and the fusion can satisfy. Right. So for example, braiding of of anions is a very good example of this, right? The S matrix. Okay, good. So that's another way to do it. So once you know you have like an EN algebra, then you can just look for this specific data out of it, and they completely characterize it. Okay, good. All right. Oh, sorry. Yeah. So it's actually written here. Yeah, exactly. So yeah. So for N plus 1 category, you need the subscript to be N plus 3. That's just that's just how it is. Okay. So are there any questions about this? So that's kind of the review part of this talk. No? Okay, good. So now our goal, so in the remaining like 20 minutes, my plan is basically tell you a generalization of this for E2 algebras. So I'm telling you that I know a way to, basically give Stashev association for E2 algebras in any higher category. Okay, and it turns out this, once you understand this example, then we can actually understand EN algebra for any N. Okay, and it's going to have this very nice structure. It turns out that it will basically also looks like a line, but instead of a line, it will become stairs. Okay, and that's what we'll be talking. Okay, once again, are there any questions before I move forward? Okay, very good. So first, let me give you a description of E2. That's okay. So basically, E2 algebra, we can think about it as they're braiding, and then we can think about it they're parameterizing basically fusions of points instead of a plane, right? So if you have points instead of a plane, they can rotate kind of around each other before fusing, and that rotation is exactly the braiding. Okay, good. But there's actually a much easier description of E2 algebra, which is given by this theorem called Dunn additivity, which says the following, which is that an E2 algebra structure is the Beaumont-Watt tensor of 2E1. Okay, but what does a Beaumont tensor mean? It just means, so let me just tell you heuristically, it just means that E2 algebra is two commuting E1 algebra structure. Okay, it means that it means that it's equivalent to give you one E1 algebra structure and give you another one and ask for all the operation commutes. Okay, and all the operation commutes means kind of things like this. It means that A, so let's say star and tensor are my two multiplication. I'm asking for A star B tensor C star D is equal. Again, equal in this high categorical world just means you actually have to give me a homotopy, and then just write equal now to A tensor C star, yeah, B tensor D. Yeah, so things like this where you can kind of exchange star and tensor is exactly what it means. If you have seen this before, this shows up in a very well-known kind of argument called the Eckmann-Hilton principle. I think I get this right. It's either the Eckmann-Hilton principle or the Eckmann-Hilton argument, and they are not the same thing. This is one of them. Okay, good. But knowing this, in some sense, so okay, great. So we know E2 is E1 tensor E1. And knowing this, in some sense, we already have solved our question. Why? Because I just told you that each E1 has a filtration by AN, right? That filter to it. Well, what does that mean? It means that E2 has a filtration by just, pairwise, AK1 and AK2 structure, right? Basically, because you think about it, you have a line as a filtration, you have another line as a filtration, tensor them together, I have a plane that filters up to E2, right? Okay, and I'm done, right? So basically, we know that, yeah, basically what it means is that if I thought about filling in E1, as I said before, it's like going up, say, for example, in this direction, right? I just go up, then I basically have to satisfy status hedron, and now I just have to kind of do that in a whole plane, right? I will have to go up and also go to the right, and when I go to infinity, then basically I have an E2 structure. Okay, so yeah, so a priori we already have my answer, but it's as we will see very soon, is kind of like really overdoing it. Okay, and in fact, again, so I see that I'm already kind of a little bit on a time constraint, so let me kind of spoil and give the answer right away. So yeah, but I hope that we can get to the end. But basically, I'm going to show you that instead of filling in this entire plane, all you have to do is actually just walking up a ladder, and in fact, it's kind of the central ladder of this. Okay. So as long as you're walking up this ladder, you can actually already get to E2. But again, that's kind of mysterious. I will spend the rest of the talk getting into this. But that would be the main question on this talk. Okay, good. So the first thing I want to say is that, okay, great. So taking a step back, we have to fill out this entire plane, right? So, but now I know that when I restrict to M categories, I don't have to fill out the whole plane because up to some point, it will just become all trivial, right? Basically, the cells are too high dimensional, it will be all trivial. If you just do a dimension counting, these are exactly the lines you're going to get. So for one category, then you have to stop here. Okay, so as long as you fill in all of these dots compatibly, you're done. For two category, you have to fill up here, and you basically just get these shells. You get this like this anti-diagonal blocks. Okay, so again, that's just coming from dimension counting. So basically, once you're outside of these shells, then basically you're gonna like ask to like fill in a 2D or something, and in one category, all 2Ds are contractible. Basically, you can always fill that. Okay, so does that make sense, everyone? So this is kind of our first approximation. Okay, just for sanity check, let's think about this example. So instead of a one category, so for example, like sets. So this is saying that to define a E2 algebra on a set X, what I need is I need two multiplication. I need X tensor. Here's one multiplication. Then I have this one. So I guess I'll call it blue. So this is X star, okay? And then they both have to satisfy associativity, right? So yeah, so this comes with associativity. And star also comes with its own associativity. And I need them to distribute over each other. So this is, again, the same form as I wrote before. So X tensor Y, star z tensor w is equal to x star z tensor y star w. Okay. So that's what it means. So using this diagram, that's what it takes to define E2 algebra on a set. Okay, I'm just kind of spelling out what those dots actually represent. Okay. But you might already see that's too much data, because remember what I told you from the beginning, E2 algebra is just, for sets, it's just a symmetric monoidal structure, right? So the only data you need is just x, you need tensor, and you need to know the fact that x times y is equal to, I guess, x tensor y is equal to y tensor x. Right? That's what it means to be a monoid, basically, a commutative monoid set. Okay. In particular, you definitely did not need two different algebra structures, right? The Eckmann-Hilton principle, this principle will actually tell you that they're the same structure. And moreover, yeah. Let me just see. Okay. So we know basically just from this very just observation, we see that this is way too much data than what's actually necessary to define a E2 structure. Okay, good. So now let me actually revisit what the Eckmann-Hilton argument. So actually confused. Maybe this is the argument. Okay. Well, I should have figured this out, but maybe this is the argument and not the principle. I'm gonna erase this. Sorry about that. It's one or the other. I just always get confused. Good. Okay, here we go. So the Eckmann-Hilton argument. So let me try to review what the Eckmann-Hilton argument is. So it says that if I have two unit of binary operation, so two A2 structures, right? Here's one of them, here's the other one, such that they distribute of each other, and that's exactly the A2 tensor A2 dot, right? Then the following is holds. The first thing is that the two multiplications are the same. That's one of the statements coming from this, which might be surprising. Again, it's a very standard argument. Furthermore, the units are the same. That means that they're the same as unit of A2 algebras. Okay, so this two structure, they're the same structure. Okay, there's no difference between them. Moreover, importantly, it also implies that both of these multiplications, they're the same, but both of them are actually associative. Okay, what does that mean? So let's take a pause here. I didn't actually assume associativity on those two multiplications, but this, if we just use this A2 tensor A2 structure, it will actually implies it's associative. Okay, so basically that's kind of an amazing thing that happens here, which is that commutativity actually implies associativity. And it's actually very easy. All I have to do is I just have to set y to be 1, and you can see. Yeah. And you can see basically here you have x tensor z tensor w, again, they're the same multiplication. And here you have, so here you have x tensor z tensor w, but here you have x tensor z tensor w, aka is associative, right? Okay. But moreover, right, that's kind of the punchline. What people normally think about it is that it actually means the operation is commutative, aka A2, aka in this case, A infinity. Okay. But drawing out, here's kind of the interesting thing about it, which is that this A2 tensor A2 structure, right? So that just means two multiplication that distributes of each other actually implies associativity, which are these A3 tensor A1 structure. So remember, A1 does nothing. So this is just A3 structures. Okay. So you say actually, you kind of, if you have a point in the middle, it actually like implies points on the same antidiagonal and far away. Does that make sense, everyone? Okay. And that's really why that's kind of the reason why basically if you want the commutativity, I just have to make sure basically it's commutative and then kind of it takes care of the associativity. Okay. And once I want to be clear, once I say commutative, I mean in this form. If I just have x tensor y equal to y tensor x, that wouldn't do it. You have to do in kind of this 4-element form. Good. But that's the original Eckmann-Hilton argument, and this is kind of how we interpret it. Okay. So now let me move up to something maybe fancier, so more categorical. Is let me tell a little bit about let me argue that this actually pattern persists. This kind of pushing off on the diagonal persists. Let's consider A3 tensor A2 structure. Okay. So now this diagram actually takes a little bit to work out, but let me tell you what it is. It involves basically, so once you have A2 tensor A2, in this form, what you have is you basically have braids that looks like this. I have these braidings, okay? And now what A3 tensor A2 imply, again, is actually a little bit hard to work out, but it basically has 6 strands. Okay, so you take 6 strands. Here the six strands, and here you see that I'm kind of using the braiding one over the other, but I'm doing it slightly differently on both sides. Right, but again, it's kind of complicated. It has 6 different strands. Right, a lot of things are kind of going on. But let me tell you something maybe miraculous, which is that this is exactly equivalent to the 2 hexagon axioms at the same time. It's actually equivalent to both of them, presents both of them at the same time. And by the way, that's a remark. A braiding model structure is just an A3 tensor A2 structure. That's something we use in the paper mentioned above. Let me show you how. Sorry. So I didn't write it down below. But basically, the idea is very simple. All you have to do is, again, I'm going to plug in units into some of these strings. So for example, if I plug units into, let's say if I plug unit into this one, and also this one. No, sorry. Yeah, if I plug unit into this one, then let's think about what happened. Sorry, only the first string is good. Yeah, exactly. So let's think about what happens if I plug the units here. So that means that this braiding kind of disappears. And what I have down below is I just have one strand braids under 2 very quickly. Right? But now let's come back to this picture. So again, I'm making this strand invisible. But then here you see this under strand braids over one, then braids over the other one separately. Right? And that's exactly this hexagon axiom. Right? And now if I don't take this strand to be invisible, if I take this another choice I can make to be invisible, I exactly get this hexagon. And on the other way, you can actually just kind of combine both the hexagon together to prove this logic diagram. Okay. So again, these are the kind of strands I'll be considering. And let me just remark, this is the kind of first starting point of how it differs from kind of the classical way we define braiding model structure. The idea is that I'm going to basically only use one diagram each time. But that diagram is going to be much larger than the ones we normally see, but we'll only need one of them each time, and it's going to be equivalent to the ones we normally see. Good. But now I claim there's still a push-up effect. If I have this A3 tensor A2 structure, it's going to imply, as I've written here, this A4 tensor A1. So if you remember what the A4 tensor A1 structure is, this is the hexagon. The claim is that the braiding actually implies the pentagon axiom. Okay? And you do it just by blanking out 2 of the things. Okay, I will leave it as an exercise, but it does follow immediately. Okay, so you see, when I blank out these 2 things, nothing is braiding over each other now, but kind of the way they multiply are different. And if you work out what it implies, it's exactly asking for the hexagon, pentagon axiom. Right. So by the way, that's a fun fact, which is that I think on the Wikipedia page, it actually does also explicitly tells you once you have the hexagon axioms, the pentagon axiom is implied by that. So that's a condition, a braiding monoidal, especially just a monoidal category should hold, but it's automatically implied by the hexagon axioms. Okay, but let me just call that Eckmann-Hilton number 1, which is that basically these diagonal pieces, the piece that's very much about commutativity, actually implies the off-diagonal pieces. Okay, and as a corollary to that, it follows that, so for example, for one category, I just need, for one category, I just need everything behind under this, but I don't need these 2 dots anymore. These 2 dots are automatically satisfied. The only dots I need are these central ones. Right? Once I have these, the other ones are implied. Right? And for a 3 category, I also need to include these 2 dots. Right? And for a 4 category, I need to include this dot. And then these dots. Right? And I'm done. So you see that's already much closer to the stair that I drew before, except that basically I think when m is odd or even whatever, I actually have 2 copies rather than just 1. Right? So now all I have to argue for is actually eliminate them. Right? So you see in the even case, you see there are these two dots and they're kind of like, yeah, and I kind of just want one of them. All right. So let's think about this very baby case. So again, remember what this is asking. This is asking you have like a set, whatever, algebra, an object C together with two unit structure on it, right? But moreover, they actually satisfy the equation in the Eckmann-Hilton argument, right? Remember, one consequence of the Eckmann-Hilton argument tells you that the two A2 structures are actually the same. They're equivalent to each other, right? That's a very classical part. That's probably the most important part of the Eckmann-Hilton argument, right? And I'm just going to represent this as this blue arrow right now, okay? So it turns out that basically those two dots are, actually, it's not necessary to satisfy both of them. You just pick one of them and the other one just a mirror copy of it, okay? And now let's go up a little bit more and let's try to consider this situation. Okay, so remember this is A3 tensor A2, and this is A2 tensor A3. And see, are they kind of equivalent to each other? And the answer is yes. So if actually, so it takes a little bit even more work, but you can actually write down what those two dots mean. Okay, you see again, they are very similar diagrams, except basically this, you kind of raise this one above the other one. Okay, on those diagrams. So they are not the same. By the way, there's a symmetry between them. You can get this diagram from this diagram by doing what? By first flipping it and then switch the order. Okay, so there's definitely a reason why that's the case. It's coming from a symmetry of E2. I don't want to get into it. But here's the claim. Those two diagrams, while they're not the same, implies each other. Why? Well, because they're both just equivalent to the classical notion of the two hexagon axioms. You can recover hexagon from both of them, and you can also imply hexagon for both of them. And very much, if you look at the hexagon axioms, it's kind of symmetric. Okay. So it follows that these two dots are actually equivalent to each other. Okay. So here's the second Eckmann-Hilton argument, which tells us that kind of on the even cases, we have two of them split, they're always going to be equivalent to each other. Okay. So once you get one, it automatically implies the other. And in fact, uniquely identifies what the other dot has to be. Okay. So combine this push-off effect, which I call Eckmann-Hilton 1, together with this kind of symmetry. So what's secretly happening is actually, by the way, there's a symmetry. There's kind of like a Z2 flipping symmetry around the diagonal. Okay. So because of these two effects, it actually follows that basically, for example, if I want to stay within one category, all I need is first I need to give a unit, I give you a multiplication, and I check that the multiplication satisfies the Eckmann-Hilton argument with itself. Because this dot is just itself, right? And then for a two category, well, after I get remember, this is the braiding, all I need to do is to check one of the two fancy, 6-strand accents. Just pick one, any one of them work. Okay, and in fact, they're equivalent to each other. So just pick one of them. And after that, you have to check so now for a 3 category, all you have to do is after you get this, you check, you have to check this A3 tensor A3 structure, which turns out to be, I think, 9 strands. So it's like some 9-strand cube shape. Okay, it's like 2-dimensional. And so here, for example, here's I guess an exercise which is actually verified that single 9-strand axiom corresponds to all 3 or all 4 of the standard Brady-Monod 2-category axiom. Okay, that's something you can check.
I was going to ask about that at some point. Is this where your sort of suppressed unit laws come in order to check that the large axiom becomes equivalent to the smaller ones?
Very good. So first of all, David, it's very nice to see you. I haven't talked with you in forever. I've been suppressing the unit in the story. Let me see. Okay, sorry.
Yeah, I mean, I'm fine with it, but do you need it to get back from the big axiom to the small one?
Yes, you plug in units. Yes, if that's what
okay.
It's always plugging units. Yeah. So again, so maybe one thing I do want to remark is that none of these things work if I work in a non-unital setting. If I don't assume my objects satisfy units, then none of this breaks. It turns out that the most crucial fact about how to prove any of this is assuming they're unital. Okay, but that's a very subtle thing. I don't want to talk too much about it. I just want to kind of paint a nice story today. Okay, but I'm happy if you have any question, I'm happy to talk more. Okay, but you see, you can just keep going up, right? So for 4 category, I just need to get to this point. Oh, shit. Right? 5 category this point, 6 category this point, right? And again, all of these points, I want to be very clear about this. You can very much write down diagram to them. Okay, I'm not saying that if you have explicit category, you can actually work it out because they're so big, but you can write down diagram for them. Okay, I can definitely. I actually, in fact, plan to do that, which is actually to compute what all those polytopes are. You can very much write them down. Okay, again, there are a lot of strands together, but it's explicit. It's very explicit. Okay, and another benefit is that this is it's just one diagram. You don't need 3, you don't need 4. I don't need to worry about how many diagrams my breaking point of 3 category or 4 category needs. It just needs 1. But it's already big. But you just need 1. Good. So with this in mind, so I hope this still works, right? So again, you're just going up this ladder, right? Every time you go up from 1 category to 2 category, you just want to increase one of your number plus 1, and you want to increase in a way that hugs the center. Right, so for example, it's 3, 2, you want to increase the lesser one. Okay, and when you get to 3, 3, it doesn't matter, just pick one. Right, then to 4, 3, you go further, you want to pick the lesser one, so 4, 4. Okay, so now, yeah, and now this is the slogan, which is that to define E2 algebra in M category, you just kind of go up this AK1 tensor AK2 plane, but hugs at the just go one every time you increase by 1, just go up this thing one more time as possible. Okay, and more generally, this result even holds for En. So remember that E2 is E1 tensor E1. En is just n copies, right? Just inductively, it turns out that En, the additivity tells us n copies of it. And what you want to do again is literally the same thing. You just hug basically the diagonal as close as you can. You basically want to get all the commutativity you can, and that's going to take care of everything else. So for example, an E3 algebra in 1 cat is just a A2 tensor A2. Tensor, the last A1 doesn't really matter. Okay, and that's a semblance of the fact that E2 and E3 and infinity are the same in a 1 category. You see, that's a corollary. Okay, but now to get to a 2 category, what you need is I need E2 tensor E2 A2 tensor A2 tensor A2, and basically you can think about the last A2 just asking the braiding to be symmetric. Okay, but again, I now I have an algorithm to do this for any n category, because for a 3 category, I just bump any of these number up. I just pick the first one, but it doesn't really matter. There's a S3 symmetry acting on this like this 3-dimensional lattice, and yeah, it respects that. Okay, but now for 4 category, I already bump up 3, so I need to increase one of these. I just increase this one. So it's 3, 3, 2. Again, it doesn't matter. Now for 5 category, I already bump up 2 of them. I need to bump up the last one. Okay, and then you just continue. It's now it's just a ladder in this 3-dimensional space. All right, bye, David. Okay, and now this is the main result of the theorem, which is the following. Okay, yeah. Okay, and again, like it's just written with a little bit more numbers, but it literally expresses the exact same thing as what I said before. In particular, this connectivity only depends on the first number and how many of the first ones are equal. Oh, the minimum number and how many of them are equal. Basically, if I can try to bump this number up to however I want, it doesn't matter. It will give me the same thing. I have to hug the diagonal. The only way I can increase is by bringing the minimum up. So it depends on this number and how many of them are the minimum. Yeah, and that's the main theorem of the paper. Okay, good. Yeah, and that concludes the talk.
Okay, let's thank Leon. I know that you have a time constraint, so maybe if you have to go.
Take 2 minutes. One question.
Yeah, okay. So let's take one question and then everyone else can put theirs in the Discord.
Yeah. Yes.
I'll make a thread.
So, maybe can I hog this? So okay, Leon, thank you. This is really cool.
Yeah, thank you.
But also, let's say I have a En object in M categories, right? And I want to look at its humps. Then I know that it should be En plus 1. It has an En plus 1 structure.
Yes.
Yeah. So can I see that in the grid that you've written down? like a T3?
I don't really know. The only, I mean, I'm not sure how relevant that is to this, just because you have an EN algebra structure, and then you have an E1 monoidal structure. They're compatible. You get a bottom additivity EN+1. I don't see like how that interact too much with this. That seems like just a tautological thing from additivity.
Right, because there's also another way to kind of indirectly define kind of higher modality, which is to just deloop it all the way to as much as you can, and then just use higher categories to do that. So I think that
absolutely. So this is similar. This is also, you can think about the exploration of the high category. But you know, like, I know what the infinite n category is. But if you ask me to actually define a n category, I personally have quite a bit of trouble, because actually the compositivity of that requires a lot of higher things.
Especially especially I want to, like, it's one of the puzzling things that me and David was thinking about. It's like, I have a braided 2 category, and I look at its harms. So is it symmetric or is it syleptic? Like, according to the latter, it should be syleptic, but
it should be syleptic.
I don't know. It's weird. It's weird.
Yeah,
like, it seems
those are things that are subtle. Yeah, exactly.
Yeah. So.
Great. I think thank you for the questions, and again, you can ask me on Discord anytime, but I do have to run.
Okay, thank you, Leon.
All right, bye. Thank you for coming, everyone.
Thanks, Leon.
Yeah.
Cheers.